So, in continuation of our work on matrices, today we're going to go over some properties of matrices. So quite a few definitions, and then you're going to see how we can do certain operations with them, and when we can't do certain operations with them. So we're going to learn all about that today. All right, just a quick little review. When you have a matrix and you just want to denote generic elements in the matrix, you can use like a little lowercase letter like A, and then you can use a little subscript of two numbers where the first number is the row and the second number is the column. So again, RC, like RC Cola, or like an RC car or something like that. Of course, I sound really old-fashioned when I say RC Cola, but that's the idea. So like in row 1, A11 is row 1, column 1. It's the element in row 1, column 1. A12 is the element in row 1, column 2. A13 is the element in row 1, column 3, and so on. So all the way across there, you would have a 1 and then whatever the column number is. And then going down, like row 2, so now you'd have A sub 2, 1, A sub 2, 2, A sub 2, 3, and so forth, and etc. In the columns, like the first column, the second number is always going to be a 1. In the second column, the second number is always going to be a 2, and so on. So that's just a quick little review there. So. Now, we'll often also use capital letters to name the matrix, like I used a capital A there. Now, a square matrix is an n by n matrix where the number of rows and number of columns are equal. So it looks kind of like a square. The dimensions going across and going down are the same. Sorry, I just bumped my printer and the whole tray fell off. Okay. So square matrix, it'll be, it's like a square where the length and width are the same. Same idea here. The number of rows, number of columns is the same. Row matrix is a matrix with just one row. And then with that in mind, you can probably guess what a column matrix is. I'll give you 3 guesses, and the first 2 don't count. So column matrix with just one column. Okay, so we talked about square matrix where the number of rows and number of columns is the same. But we can also talk about matrices themselves being equal. So this is all some definitions just to kind of keep in mind moving forward. Matrices are equal if they have the same dimension so number of rows by number of columns. And corresponding elements are equal. Okay, so I think that's all I can squeeze into that slide. So these are some definitions and concepts to keep in mind as we start getting into properties. All right, so examples of equal matrices. If 2 matrices are equal, then the elements in the same exact positions are going to be the same. So like take these two matrices for example. A sub 1, 1, the element in row 1, column 1, is 5 for both matrices. That matches up. A sub 1, 2 is negative 3 in both matrices. A sub 2, 1 is 8 in both matrices. A sub 2, 2 is 1 in both matrices. So not only do we have the number of rows, number of columns the same, like each of these is a 2 by 2, and it turns out each of these is a square matrix. That's not, this being square is not necessary, but it just turns out that way. But but the corresponding elements in the same exact positions, are the same. So that tells us they're equal. Whereas if you had something like this, these are not equal. Because even though they're both 2 by 2, and even though they both have the same elements, notice that in A sub 2, 1, you have an 8 in one matrix and a 1 in the other. And notice that in A sub 2, 2, you have a 1 in the first matrix and an 8 in the other. So in those positions, you do not have identical elements in those corresponding positions. So those two are not equal. But you can also use this concept to help you to look at two matrices and try to decide how to fill in the blanks. Like let's say you have a matrix with A, B, negative 5, 0. And we know that it equals the matrix with negative 3, 9, C, and D. Since we know that they're equal, we can look at it, well, they're both 2 by 2. So that's good to know. 2 rows, 2 columns. So you have elements in positions, corresponding positions. So then if they're equal, then the elements in the same exact positions should be the same. So we can then say, well, that tells us that this A and this negative 3 that are both in A sub 1, 1, they have to be the same. So A has to equal negative 3. Or we can say this B and this 9 are both in A sub 1, 2. So that tells us B has to equal 9. The negative 5 and the C are both in A sub 2, 1. So C has to be negative 5. And then the 0 and the D are in A sub 2, 2. So D has to be 0. So we can see that those match up and they're equal, so then those values have to be the same. Whereas in this example, they're trying to be tricky. They say, what if the matrix with xy equals this matrix with 3, negative 5? We have a 1 by 2, 1 row, 2 columns, and a 2 by 1, 2 rows, 1 column. This does not have elements in all the same exact places. Like the first matrix has an element in A sub 1, 2. The second matrix does not. The second matrix has an element in A sub 2, 1. First matrix does not. So this statement can never be true. Because you have to have all those positions exactly matching up and having exactly the same values. Okay, so that's equality. What about addition of matrices? To add two matrices of the same dimension, add corresponding elements. Only matrices of the same dimension can be added. So in other words, they have to have the same number of rows and same number of columns. So let's say you have 3, -8, -4, 6, and you're adding with 7, -5, 10, -6. You want to see what that equals. So you take elements that are in the same positions and you add them and then put them back into that position. Like you can take the 3 and the 7, add those together, and get 10. You can take the -8, -5, add those together, get -13. You can take the -4 and 10, add those together, get 6. You can take the 6 and -6 and add those together, and get 0. But this worked. You had a 2 by 2 and another 2 by 2. So as long as your dimensions are the same, like the dimensions, 2 by 2, 2 by 2, the number of rows, number of columns has to be the same in order for this to work. If they're not, then you can't do it. All right, another example. Let's say you have this nice little column matrix with -9, 7, 6, -3. I called it a column matrix because it only has one column. It has 4 rows, that's all right. Just column and column matrix just has one column. Let's add that to another column matrix. -9, 5, -6, and 10. So the answer is going to be a column matrix with four rows, 1 column. Because we have a 4 by 1 here, and we have a 4 by 1 here, so this is perfectly fine. So we can add up the -9 and the -9, get -18. We can add the 7 and 5, get 12. We can add the 6 and -6, get 0. And we can add the -3 and the 10 and get 7. So there you go. And again, they have to have the same dimension. If they have different dimensions, then they can't be added. Like if they give you an example that's 2 rows and 3 columns and want you to add that to something that's 3 rows and 2 columns, that's not going to work. So it has to be the same dimension. Like let's say, for example, you have this one, 3, -1, 6, 0, 7, -2, and you want to try to add that with 4, 8, 3, -1, -5, 2. So this one is 2 by 3, this one is 3 by 2. Those cannot be added. Because of those different dimensions. Okay. A special matrix called the zero matrix is a matrix containing only zeros for elements. If you take matrix A and add that with the negation of matrix A, you will get that zero matrix. For example, let's say matrix A has 4, -7, 6, 5. Then negation of A will be -4, +7, -6, -5. And if you go ahead and add those up, you're going to get 0, 0, 0, 0. Because the 4 plus the -4 will give you this 0 here. The -7 and the +7 will give you this 0 here. The 6 and -6 will give you this 0 here. And the 5 and -5 will give you this 0 here. So you end up with a lovely 0 matrix. And that hints at subtraction of matrices too. If A and B are matrices of the same dimension, then A minus B is the same thing as adding A and -B. Just like with numbers. So you're subtracting, basically subtracting the corresponding elements. But again, you have to have the matrices of the same dimension. Like let's say you have a matrix with 8, -9, -6, 2, and you're trying to subtract the matrix with -8, 4, -7, and 11. Okay, these are both 2 by 2, so we're good there. They have to have the same dimensions. And like for your, like in A sub 1, 1, you have 8 and -8, and you're subtracting those. So 8 minus -8, which becomes 8 plus 8, or 16. Or you got -9 minus 4 in A sub 1, 2. So that becomes -13. In A sub 2, 2, you got, or A sub 2, 1, sorry. You got -6 minus -7. That becomes 1. And in A sub 2, 2, you have 2 minus 11. That becomes -9. So just make sure to pay attention to that sign in the middle. Remember, it's just like subtracting integers in general. Just make sure you're subtracting the elements that are in the same positions. And again, they have to be the same dimension. If they're different dimensions, you can't subtract them. All right. Let's next look at scalar multiplication. So a scalar is just, some number. It's not a matrix. It's some number outside of a matrix. The product of a scalar, k, and a matrix X is the matrix KX. So each element is K times the corresponding element of X. All right, so let's say, for example, you have the scalar -3, and you want to multiply that with the matrix 2, -5, -4, 0. So what you do is you take that scalar of -3 and you multiply it with each element in that matrix. So the resulting matrix is -6, 15, 12, 0. And your scalar can be a fraction too. It doesn't have to be an integer. Like you could have 4/5 in front of a matrix, like -25, 10, 15, -45. And again, you're multiplying that scalar times each element and then replacing that element with the result. So like when you do 4/5 times -25, you get -20. So now -20 goes in that a sub 1, 1 position where -25 had been. 10 is in that a sub 1, 2 position. So you do 4/5 times 10 and you get 8. 15 is in a sub 2, 1 position. So you have 4/5 times 15 and get 12. And then -45 is in the a sub 2, 2 position. 4/5 times -45 is -36. And that's what goes there. So that's scalar multiplication. There's some properties I'm not going to like go into too much detail with. I'm just going to tell you what they are just so you can be aware of them. So some properties of scalar multiplication. So A and B are going to be matrices of the same dimension. And then C, D are scalars. So if you have two scalars that are being added together and then multiplied by a matrix A, you can basically use a distributive property. You can take the scalar C times the matrix A plus the scalar D times the matrix A. So you could go in and you could multiply the scalar C with the matrix, multiply the scalar D with the matrix, and then add those results together. But it can also work where, like, if you have one scalar and two matrices being added, it's like the distributive property. You can do the scalar times the first matrix plus the scalar times the second matrix. Multiplication's got a similar thing. Like if you have scalar times matrix A times another scalar, you can change the order around a little bit. Do the two scalars together, then times the matrix A. Or if you have the two scalars times matrix A, again, you can move things around a little bit and do scalar times the result after doing the other scalar times A. So that's an associative property type situation. So there you go there. I'm not going to go into any more detail than that. All right, and not only can you take a matrix and multiply it with a scalar, but you can also take matrices and multiply them together. If you want to multiply two matrices together, it's really important to look at your dimensions first to decide if they can be multiplied together or not. So let's say you have matrix A with dimensions m by n. And let's say you have matrix B with dimensions n by p. As long as the n and n inside are the same, that's good. Then the dimensions on the outside here will be the dimension of the answer. multiply the two matrices together. Now, an interesting thing, though, is like if you switch the order, matrix multiplication is not commutative. If you put matrix B first, matrix A second, notice what happens with your dimensions. The insides are not the same, so we can't multiply them. And you might be wondering, well, why is that? Like, this seems kind of out of left field. Like, why would that matter? Well, it all has to do with how matrices are multiplied. All right. Let's say you have, a matrix. Matrix A is 4, 1, -3, and 8. And let's say matrix B is 3, -4, 5, 1, 0, -6. So you have a 2 by 2, and then you have a 2 by 3. The insides are the same, so we're in business. And then the outsides, that'll be the dimension of AB. So when we multiply them together. Okay, so let's take a closer look at what happens when we multiply these together. Okay, so we're going to end up with a 2 by 3. So in our first multiplication, we will look at row 1, column 1. And what we'll do, since we're looking at row 1, column 1, our element, our result, will be in A sub 1, 1 when we write it in the answer. And what we're going to do is we're going to take the 4 times the 3 plus the 1 times the 1. So 12 plus 1, which is 13. Next, we're going to look at row 1, column 2. That's going to go in A sub 1, 2. We're going to do 4 times -4 plus 1 times 0. So that's going to give us -16. We're going to do row 1, column 3. So that's going to go in A sub 1, 3. We're going to do 4 times 5 plus 1 times -6. So 20 minus 6, which is 14. So that's what we've got so far. Then we're going to hop down to row 2. We're going to do row 2, column 1. So that's going to go in the position A sub 2, 1. We're going to have -3 times 3 plus 8 times 1. So -9 plus 8, which is -1. We're going to have, I'm trying to pick other colors here, have row 2, column 2. So it's going to go in A sub 2, 2. So it's going to be -3 times -4 plus 8 times 0, which will be 12. And then finally, row 2, column 3. So that's going to go in A sub 2, 3. We're going to do -3 times 5 plus 8 times -6. So -15 plus -48, which which will give us negative 63. And there you have it. So we just multiplied two matrices together. We multiplied A times B. Now notice that you cannot do B times A in this example. Because if you did B times A, your dimensions would be 2 by 3 and then 2 by 2. Those inner numbers would not be the same. You'd have a 3 and a 2. So that's an example that shows that matrix multiplication is not commutative. AB not equal to BA. Let's do another example so you can see it. All right, let's say you have matrix C. That is 2, negative 5, negative 6, 1. And let's say you have matrix D. That's 3, negative 4, 2, 3. So let's do C times D first, because you have a 2 by 2 and a 2 by 2. They're square matrices. If you do C times D, you got to do row 1 times column 1. Well, I shouldn't say like that, but you have to do like row 1 and column 1. You have to multiply and add. So you're going to have, what, 6 and minus 10. So that's going to be negative 4. Then you have row 1 and column 2. So that's going to be negative 8 minus 15. So it's negative 23. Then you're going to have row 2 in column 1. So that's going to be negative 18 plus 2, which is negative 16. And then row 2 in column 2. So it's going to be 24 plus 3, which is 27. So that's how that's going to turn out. Let's do it the other direction. I'm going to go to a new slide and rewrite. Let's rewrite D it's the same matrix from earlier. You got the 3, negative 4, 2, and 3. And then we're going to multiply that with C. We're going to do D times C and see what that comes out to. C was 2, negative 5, negative 6, and 1. So row 1 times column 1, I'm going to have 6 plus 24, which is 30. Row 1 times column 2, I'm going to have negative 15 and negative 4, which is negative 19. Row 2, column 1, I'm going to have 4 and negative 18, so that's negative 14. Row 2, column 2, I'm going to have negative 10 and 3, which is negative 7. And again, that the CD and DC are not equal to each other. Because remember, CD, the answer had been negative 4, negative 23, negative 16, and 27. While DC we now know to be 30, negative 19, negative 14, negative 7. So actually every position the numbers do not match. A sub 1, 1 do not match. A sub 1, 2 do not match. A sub 2, 1 do not match. A sub 2, 2 do not match. So no commutative property here. But that's how you multiply. Now matrix multiplication does have the associative and distributive properties. I'm not going to go into details and do examples, but just know that it does have associative and distributive properties. So like, let's say you have A, B, C matrices. And as long as, products and sums exist, if these products and sums exist, then the product of AB, then C, it's the same thing as the product of A and then BC. So long as the product AB exists, as long as the product BC exists, all of that, you can regroup it. Dissociative property. Distributive, as long as you can add B and C together, and as long as you can multiply A with that result, then, and as long as AB and AC exist, then you have the distributive property. Or the other direction, like let's say B plus C is first, then times A, you can distribute that as well. So I'm not going to go through and prove or do a bunch of examples, but just know that those properties do exist versus commutative not existing. We'll talk about identity and inverse properties in a future video. Those come up too. All right, so there's that. Maybe we should conclude with a little word problem. I know everybody likes to see examples of word problems, especially when they end up coming up in your homework. So let's see if we can do an example of one. Let's see, a contractor builds three kinds of houses, three models of houses. A, B, C. Okay. There are two styles. Colonial and ranch. If you watch a lot of HGTV, you probably know what these styles generally look like. I'm still a little confused by it at times. Sometimes they'll say it's a ranch, and I'm like, what is it? But whatever. Okay. They're going to building 150 houses. Okay, matrix M is going to show us the distribution of houses by model and style. So the rows are going to be the models. And then the columns are going to be the styles, colonial and ranch. We're going to have a matrix here. We have 10, 15, 25, and we have 30, 25, and 45. So in other words, for model A, there's 10 colonial style and 30 ranch style. For model B, there's 15 colonial style, 25 ranch style. And for model C, there's 25 colonial, 45 ranch. Okay, so that's the distribution. All right, what other information do they give us? Okay, so matrix Q is going to give us the information for the amounts for each of the main materials used depending on the style of house. All right, so styles of houses were colonial and ranch. And what materials are being used? Well, we have concrete, we have lumber, we have brick, we have shingles. So you can make a little 2x4 matrix for that. Okay, so the colonial style, I think we're going by, like, it says it's the amounts. I'm trying to figure out if that's like pounds and numbers. Like concrete is probably, what, 10 pounds? I don't know. It's not very clear on that exactly. So whatever units of concrete. So colonial takes 10 units of concrete. Ranch takes 50 units of concrete. Or like the colonial takes 0 bricks. Ranch takes 20 units of bricks. That kind of thing. It's whatever their units are. Literally, it doesn't take literally 2 shingles on these houses. It's 2 units, whatever size units those are. Then R is going to give us each of the materials and the cost per unit. So this is actually a 4x1 matrix. I'm running out of space here. I apologize. I'm trying to squeeze all this in. This is the cost per unit. And we're dealing with the concrete, lumber, brick, and shingles. I'm just going to abbreviate to squeeze that in. So that's our main matrices we have going on here. So we're interested in finding out, like, what is the total cost of materials for all houses of each model? Then how much of each of the 4 kinds of material must be ordered? What is the total cost of materials? So we're going to use this information to help us define that, figure out what's going on here. Okay, so for the first question, total cost of materials for all houses of each model. Okay, to find that, we're going to need to multiply P and Q together. Okay, so P, we had models A, B, C, colonial, and ranch. We had the numbers of those. That was 10, 15, 25, 30, 25, 45. Oh, I guess it's M by Q because we changed it to M for this example. Sorry, earlier, another example, it was P, but M and Q. Okay, so we're going to multiply that. So the numbers of each model of each type, and we're going to multiply that with those costs. So we're going to take that other matrix where we had colonial and ranch, and then it was like 10, 50, 2, 1, 0, 20, 2, 2 for concrete, lumber, brick, and shingles. So we're multiplying those together. So we have, what, a 3 by 2 that we're multiplying with a 2 by 4. So this will be fine because 2 and 2 and the insides are the same. Our resulting matrix should be a 3 by 4. All right, so the result there, I'm gonna make this good size. We'll have 100 plus 1,500, so that's what, 1,600? And we'll have 20 plus 30 is 50. 0 plus 600 is 600. 20 plus 60 is 80. And we'll have 150 plus, oh gosh, I feel like I need my calculator here. I don't want to trust my head. Plus, so plus 1250, so we're going to get 1,400 here. And then 30 plus 25 should be 55. 0 plus 500. Then 30 plus 50 is 80. Okay. Then we'll have 250. Oh my goodness. 25 times 50, 250 plus 1250, so 1500 here. Then we'll have 50 plus 45 is 95. Then we'll have 0 plus 900, so 900. And then we'll have 50 plus 90 is 140. Okay. So that's the total amount of material needed for all houses of each model, because we just took each model and the types of houses and we multiplied that with the types of houses and the materials needed, how much of the materials were needed. So that gave us that nice cross there with the two matrices, gave us what was going on there. So between models A, B, C, we now know how much concrete, lumber, brick, and shingles are needed. So that's what that was giving us. Okay, so then the next step wants to know how much of each of the 4 kinds of material must be ordered. Oh, sorry. No, we just figured that out. Oh, we're already doing that. So that was the amount of material needed for all houses of each model. Then we need to multiply by our cost matrix to see, well, what's the total cost for the materials for each model. So we're going to multiply this now with that cost per unit. So that was the 20, so we had the concrete, lumber, brick, and shingles, and the dollars per unit. So we had the 20, the 180, the 60, and the 25. So we had a 3 by 4 and we have a 4 by 1. So we should end up with a 3 by 1. So a column matrix. Yikes, that's going to be a lot of computation, isn't it? That should be fun. Okay, so 1600 times 20 plus 50 times 180 plus 600 times 60 plus 80 times 25. And that equals 79,000. Okay, so for model A, we're looking at $79,000 total for our costs for all the materials. Model B, we've got 1,400 times 20 plus 55 times 180 plus 500 times 60 plus 80 times 25. And we get $69,900 for that one. Then model C, we have 1,500 times 20 plus 95 times 180 plus 900 times 60 plus 140 times 25. All right, that did not work out right. I got too low. Let me do the math again. Maybe I messed up when I was typing this in. Okay, 1,500 times 20 plus 95 times 180 plus 900 times 60 plus 140 times 25. Yeah, I'm still $20,000 short. Where did I goof? That is the question. All right, so I had 25, 45. Let's see here. I'm looking at just for the C. So let's do that math again further back. All right, 25 times 10 plus 45 times 50. That was, oh, this should have been 2,500 over here. Woo, that explains that part. I should probably double check the others though. See, I trusted my head. You probably were following along going, oh, Miss Schofield, probably yelling at me. But I can't hear you. 50 plus 45 is 95, that works. And then 0 plus, that should work. Okay, let me try it again then. All right, 2,500 times 20 plus 95 times 180 plus 900 times 60 plus 140 times 25. Much better. 124,600. Woo! All right, so there you go. So that's the total cost of those materials. If you wanted to go further and figure out like how many units of concrete, how many units of lumber, how many units of brick, how many units of shingles, you could go back to, excuse me, what they call matrix T. Or they call it matrix T, but you could go back and look at your MQ result and you could add those up. So like if you go back over here to the far left, you could add up the results from your MQ. And you can add up the columns. And that'll tell you just how much of each you need. So how much concrete, how much lumber, how much brick, and how much shingles. So if you add up all the concrete numbers, you get 5,500 units. If you add up all the lumber numbers, you get 200 units. If you add up all the brick numbers, you get 2,000 units. And if you add up all the shingles numbers, you get 300 units. So I was just going back to that matrix MQ and just each column. For the column for concrete, add up those numbers for A, B, and C for the 3 models. For lumber, add up for the 3 models. For brick, add up for the 3 models. Shingles, add up for the 3 models. And that'll tell you how many units of each material needs to be ordered. And then if you want to get the total cost of all materials, you could take that matrix that you just found and multiply by the cost per unit on those. I'm going to leave that alone. Like the cost per unit was like 20 for concrete, 180 for lumber, 60 for brick, 25 for shingles. So you could take that matrix we just found and multiply that with the cost per unit to see, well, how much is it going to cost. It's going to come out to a grand total to build these of $273,500. So if you go ahead and do that and try it. All right. So this is a variation of an example in the current textbook on page 958, if you're interested. I did a variation on it, but if you want to see another example, it's on pages 958, 959 of our current textbook. All right. So that is your properties of matrices. We do need to talk about the identity matrices and inverse matrices, and we will do that in the next video. So just, hang on tight. Can't wait to see you again. And that should wrap up our matrices for this course in that next video. All right, thank you for joining me again, and see you soon.